Hello everyone. Today we're going to be talking about conjugated systems, and we'll be looking at the specific, relatively simple example of this, the 1,3 diene. So before we get into this topic requires a little bit of an understanding of how hybridization works, or more of what is left behind after orbitals become hybridized. So let's take a simple example. Oh, let me start drawing. Okay. So you have carbon double bonded to carbon, and let's say there's a hydrogen coming off of each of these. So hydrogen coming off of each of these, you get the idea. So what is the hybridization of each of these carbons? Well, we look, there's 3 bonds, and at some point I'll probably make a video specific to hybridization as a review, but it's sp2. So both of these are sp2. Now what this means is there is one unhybridized p orbital left in both of these atoms. That's how the double bond is formed. You could think of it looking like this. So you have each of the carbons, and you have the sigma bonds that are sp2 hybridized, and then you have a single unhybridized p orbital on each of these carbons that each hold a single electron, and these can connect, and that's how you have the pi bond in the first place. And it's much more stable than simply having a radical sitting on each of these carbons. What this means is the electron density is being shared. The electrons are being pulled at some point in between these 2 carbons, right? But this doesn't only occur with 2 carbons. In fact, this can occur across many different carbons if certain qualifications are met. So let's look at this. I think it's 2-propanol, or I think the common name is acrolein. Is it 1, 2, 3? Oh, I added an extra thing. Alright, 2-propanol. And let's see, what pi bonds we have. So we have a pi bond here, 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 and also on oxygen. We have an extra pi bond. So this isn't only with carbon. So if we look at how many p orbitals this is, if we just draw it in this simple form, we have a p orbital here, 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 and here. And these each hold, this is where the oxygen is, each hold a single electron. But because they're all next to each other, they're all parallel, they're all able to overlap. So there's 2 qualifications that have to be met. We'll talk about that in a second. But what occurs is that the electron density is shared among all 4 p orbitals. So not just 2, it's shared between all 4. And you can see that if you think of it sort of like resonance. So this is the main major resonance structure. But if you share the electron density, we can see where the electrons go. So let's say these electrons will go here, and this electron pair will go onto the oxygen, and then you get a second structure that looks like this. So you have an oxygen with 3 lone pairs, so it has a negative charge now. You have a new double bond that's formed. That's where this lone pair went here. And now what did we leave behind? We took a lone pair. Well, now this carbon has a positive charge. And as you can probably tell, this isn't a major structure or a good structure because the carbon's positively charged and it doesn't follow the octet rule. This carbon would only have 6 electrons. And this negative charge on the oxygen isn't too good as either, but it's much more stable because it has resonance. The actual structure of the molecule is somewhere between these 2 structures. So it's able to share it's spread out its electron density. It's much more energetically favorable. So 2 qualifications have to be met in order to become a conjugated system. So one qualification is that it has to be able to donate a p orbital. Donate p orbital. And so what I mean by this one's pretty easy to understand. If you just draw a really big molecule, something like this, and you'll notice that both these carbons are sp2, 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 sp2. So all the carbons I've mentioned thus far are able to donate a p orbital. They all have an unhybridized p orbital. Then there's free rotation, so they can overlap. That's great. But the problem is this carbon here is sp3 hybridized, if you notice. That means there is no p orbital that is available to accept electrons. So this system isn't conjugated. There's a little bit of jumping around that you could possibly have here, and then this could hop on as a radical, but it's not very good. This isn't a completely conjugated system. It stops here. So if you ever see a carbon that is not hybridized, that's where you have to stop conjugating and sharing electron density. The other qualification that has to be met is that the structure has to be able to overlap. In order to overlap, so the structure, by structure I meant the p orbitals that share electron density have to overlap. So in order to overlap, you have to be parallel. Parallel. So in these structures, so in the structure we had before, that was fine because the acrolein could undergo free rotation. So every p orbital could go in the same direction, just let's say the y direction. But let's say we have a structure like this. So is this a conjugated system or not? Well, it follows the first rule. It can donate a p orbital. This structure, if we assume has two hydrogens, has one p orbital to donate. This has one p orbital to donate. This actually has two. This is sp hybridized. So why doesn't this work? I'll give it away. It doesn't work. Well, it follows the being able to donate a p orbital, but is not able to overlap. So let's say this is a y direction, right? One electron's being shared. So let's say one of the p orbitals is also in that direction, in the y direction. Now if we take the last p orbital, this isn't also going to be able to be in the y direction as well. There's already a bond forming between these two. A second bond can't form. What would end up happening is we would have a radical on here. The electron in the p orbital couldn't do anything. In fact, there would be a radical on both, I believe. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4. Yeah, it'd be weird, and it wouldn't follow the octet rule. It just wouldn't work. So it just doesn't make sense. So what has to happen is this structure has to bond with the remaining unhybridized or p orbital, which could be in the z direction. Just imagine that's going like into the page. And in the same way, the last carbon will also go into the page. So there's a second double bond, so we end up with this structure. But what's the problem here? Notice if this is carbon 1, this is carbon 3, this is carbon 2 in the middle, that carbon 1 and carbon 2 overlap, carbon 3 and carbon 2 overlap with different orbitals, but carbon 1 and carbon 3 do not overlap with each other. They can't share 3 and 1 cannot share electron density with each other. Therefore, they're not a conjugated system. So those are the only two rules about whether a system can be conjugated or not. There's a few exceptions, like if you're having a polycyclic ring or something like that, but situations where you have Basically, if these two qualifications are met, you could have cations that are conjugated, you could have anions that are conjugated, even radicals that are conjugated. And I believe in the next video we're going to do example problems about this, so we can look at some of those weirder examples then.